Fantastic. So most importantly, John Ryter is one of the best lead belayers I know, and climbs with me and always gives me a great belay. And that's really the most important thing to know. But much less importantly, he's also a PhD student at MIT studying material science and does real science in contrast to most of us who do computer stuff. And we're glad to have him. So John, thank you for joining us today. And oh, I need to make you co-host actually. So this is very professional. More, make co-host. Nice. Okay, you should now be able to share screen. And John has mild COVID, so if he has brain farts, we'll forgive him. And John, thanks for presenting even in the midst of your personal experience of the pandemic. And the floor is yours.
I mean, it's round 2, I guess, technically. Are you seeing the right screen?
Whenever. Yep. Okay.
Cool. Because yeah, I managed to get COVID back in May of 2020, like right at the beginning. So I guess it's nice to now be introducing myself to a more mild version. But yeah, so yeah, as Max said, I am a PhD student at MIT in the Department of Materials Science and Engineering. But as you'll probably see, I'm not actually doing quote unquote science. I'm still doing computer stuff. So we within my advisors group, Elsa Olivetti, we do industrial ecology is sort of the like umbrella name for this branch of materials stuff, trying to understand the environmental impacts of different actions that we can take in trying to reduce the impact of industry. And so what we've done is we built a material system model of the copper supply chain that is rooted in the economic relationships between the different actors within the supply chain. And so we're going to be looking at the effects of increasing recycling. And so the sort of motivating thing here is that we have some conflicting goals around materials. Materials use is rapidly increasing and has been, as we can see on this figure on the right, gained like 2 orders of magnitude over the last 100 years or so. And of course, our materials consumption is closely tied to greenhouse gas emissions causing climate change, as well as a variety of other forms of pollution. And so as a result, we want to decouple our environmental impacts from growth. Obviously, decoupling is not unique to materials, but particularly our additional challenge here is that many of the low carbon energy transition technologies require several key materials. And so while we want to decrease our emissions, we also are needing to increase our consumption of some of these materials that also create emissions. And so the main material we'll talk about today is copper. It's useful for increasing electrification, makes up all of our electrical wiring, essentially. Some of it is aluminum, but most of it's copper. Very high electrical conductivity. And then lithium and cobalt are 2 other materials that are sort of like hot right now. They're both important for lithium-ion batteries. And so we've done a bit of work on those. Happy to talk more about them, but we'll focus on copper for today. So to decouple our environmental impacts from growth, we need some sort of mechanism for decreasing our reliance on primary material. We refer to things as primary being like virgin mined material coming from the earth, and secondary as being scrap material. And so we need a mechanism for decreasing primary material reliance on energy consumption, and recycling is a fairly like straightforward and maybe obvious solution. So recycling copper takes about 15% of the energy of primary copper. But when we increase recycling, what's actually happening, we usually think of recycled materials as having like an environmental benefit. At least that's the way things are always like advertised. But that benefit really comes from the recycled material replacing or displacing mined material. It's always a relative benefit because recycling still takes energy and has emissions. But mines don't actually like know when we've added more recyclables to the system until prices change. And also with large scale operations, they're relatively slow to respond to these price changes too. And so these two factors kind of keep recycled material from directly displacing primary or mined supply. And so this idea is similar to the rebound effect in energy efficiency, which is a fairly well documented idea that basically when things get more efficient, we use more of them. So for a fun example, like when LEDs were first introduced as light bulbs, we expected these huge energy savings because each LED consumes so much less electricity, but then it costs so much less to install lighting and cut people's power bills that people just lit more shit. And we lost about 40% of the expected energy reduction. So it's a similar idea for recycling. When we recycle more, we add more raw material to the supply chain. That causes prices to fall because there's more supply than is demanded. And this causes manufacturers to then use more of that material because it's cheaper. And so the extent to which this occurs is a function of time. So like the more rapid your increase in recycling, the more likely you are to see larger price changes. And so we want to try and quantify this rebound effect in materials. And so what we have developed is this metric called displacement. It's fairly simple. It's a measure of the efficiency of our scrap supply increase, where it's the cumulative decrease in primary production divided by the cumulative increase in secondary production. So as a quick example, if we start with some primary production, some secondary production adding to some total, and we add, say, 100 kilotons or 1,000 metric tons of secondary production, in an ideal world with displacement of D equals 1, we would just see total production remain unchanged and primary production fall by 100 kilotons. And so this is what most recycling studies are assuming, this 100% displacement. And so when we're saying, we save X tons of CO2, this is what we're assuming. But in reality, we expect things to be a little bit different. So this adding secondary material decreases prices, increases total consumption, and then mines are slower to respond, so they don't decrease their production as much as we would expect them to. And so we try to understand how this happens, how much it happens, through our fairly large model or set of models that tries to address these issues of sort of ignoring the economics of the system and just address, typically people address recycling in isolation. And so we look at each of the major commodities within the system. So ore, scrap, refined material, and fabricated goods. And we model how the production and consumption of each of these changes over time. And so many of these components are dependent on each other. So for example, refineries consume both ore or copper concentrate as well as scrap to produce a refined copper product, or just refined copper that then is made into a product by fabricators. But fabricators can also consume scrap alongside that refined product. And so we determine the extent to which fabricators use scrap and refined material from our blending optimization model, which uses scrap and refined materials, prices and compositions to determine the sort of lowest cost set of raw materials that can meet all of the composition requirements of the system. And then each of these production and consumption balances or supply-demand balances come together to generate price evolution, where prices change to minimize the difference between supply and demand. So when you have supply increase, with a constant demand, you're going to have prices fall. And so we look at sort of the prices for each of these main commodities, where refined copper has sort of just a refined price, not relative to anything. But for ore and copper concentrate, which is the concentrated version of copper ore that mines typically they do that concentration step on site, and then since copper ore is typically 1% copper, they concentrate it up to 30%, and then it's much more reasonable to try and ship it any form of distance. And so for that concentrate market, we look at the refining charges that refineries charge to mines for processing that. material. And then scrap prices, we typically actually look at the difference between refined price and scrap price because it's much more informative of what of how much scrap actually gets consumed. And so then these prices feed back into the system and determine how production and consumption evolve over time. And so that allows us to have model evolution year over year. And we also determine our overall copper demand based on these this little red box coming in from the side, the regional GDP per capita and sectoral volume predictions. So we think about the system as we will have, you know, however many million cars required per year, and the copper content of each car is going to evolve as GDP per capita changes. As we get richer, we add more copper to our cars, and then also as copper price increases, we will decrease the amount of copper in our cars by substituting aluminum in car radiators, for example. And so then we also use a method that we call material flow analysis to determine how much material is reaching end of life in any given year, to determine then how much post-consumer and post-industrial recycling is available for consumption in each year. And so material flow analysis is fairly straightforward. We take demand, assume that each sector, like cars, has a specific lifetime. That lifetime can be a distribution or just a set number. Here we use a log normal distribution. And so then in each year in the future, some fraction of that year's demand will reach end of life. And so each of these market actors, mines, refineries, scrap dealers, and manufacturers, their behavior is governed by some set of underlying models. So for mines, we have this first equation where ore grade declines over time as higher grade ore bodies are depleted. So this is like the cumulative, oh no, I lost the little exponent there, got outside the circle. But as this ore here is the cumulative ore processed by that mine. So as we increase our cumulative ore processed, we lose some ore grade as higher grade deposits are depleted. The second one is mines change their production in response to their profitability, and then they close when it maximizes their net present value, which is just their profit essentially, or cash revenues year over year, adjusted for inflation. So eventually at the end of life, their cash flows start to turn negative, and it makes more sense to close than to continue operating. So this lets us simulate all of the sub-commodities production and consumption over time. So we start in 2018, since that's where our data started. And that's where the dashed line plot is, in the plot is here. And we go out to 2040, since that's when so much of our climate action needs to happen by. And so on the left here, we look at mining production and consumption, where we break mines out into the two different types of mines that make up the copper mining system. So there's the mines that produce copper concentrate, and then there are mines that produce refined copper directly via a process called solvent extraction and electrowinning. Not super important to the overall story, but just wanted to make that differentiation. And then we also look at refined copper production and consumption, and we can see that solvent extraction and electrowinning copper produced there, as well as copper that's produced by refining copper concentrate. That's the primary refined production, and then scrap that gets refined, or recycled material that gets refined, and that's the secondary refined production.
John,
And,
how many years of data do you fit your model to before it starts making predictions? Like, do you have data from 1960 all the way until 2018 that you're fitting to, and then it's predicting after that?
I mean, it depends on which sector we're looking at. For a lot of these, we did have like 1960 to 2018.
Okay.
And like some of it we've done smaller sets and then tested against like the years in between.
Mhm.
But a lot of it is at a higher level of granularity than this is, and so we only have like for overall copper demand within different sectors like transportation and construction, etc. Like we've only got demands for like 2000 to 2014, and so that one we used like a Bayesian optimization model.
Mhm.
Yeah, for overall like copper consumption, it goes all the way back to like 1912.
Okay, but in general, things that happen after 2018 in these plots are predictive in nature, whereas things before 2018 are data, right?
Yeah, exactly.
Got it. Okay, thanks.
Yeah, so hence you don't see the massive COVID drop.
Right. Good point. Yeah.
We did like one of our assessments we did like actually plug in the like GDP and associated like shutdown information, and so we have like looked at what the effect of COVID is long term. But yeah, not shown in these like baseline plots. And so we separate scrap supply into or scrap supply and demand into scrap that's directly remelted and scrap that has to be refined first. So there's a lot of copper scrap that's of high enough quality that we don't need to refine it before we use it, and so that just gets directly reused, um, which is kind of nice. And so then we can see how each of their prices evolves over time. You can see we had a lot less price data historically. And so we look at refined price, the scrap spread, the difference between refined price and scrap price, and the refining charges, the fee that mines pay to refineries, and how those change over time. And so there are having all of these dynamic components in the model lets us see how it responds when we perturb it. And so we've done that by increasing the supply of recycling, by increasing demand for recycling, changes in trade policy, like China's ban on solid waste imports. We did COVID, and also like since there are so many different parameters and there is a good amount of uncertainty involved with so many of our parameters, we also do a sensitivity analysis, just looking at how all the different response rates within the model affect the model behavior. And so since time's pretty limited, we're just looking at how changes in the recycling supply affect the system. And mostly just we're only going to focus on the sustained recycling policy because the policy reversals just are sad and result in pretty minimal benefit and can actually cause harm. So if we go back to our decoupling impacts from growth and our time dependence in economics and slow mine response, we remember that these feedbacks and the rate of these feedbacks all play a role in what our displacement turns out to be. And so we have simulated hundreds of different recycling scenarios with different quantities and ramping up over different rates, and observe the outcomes to try and understand, how we should recycle, I guess. And so there are a couple of different ways that we could define our best case scenario. So we could either, do our highest displacement, so our most efficient recycling increase, or we can look at our highest environmental impact reduction, because these may not actually be the same since we're looking at different quantities of material. So we then incorporated a life cycle assessment on top of the model to evaluate the environmental impacts associated with each flow within the supply chain. And so we can then see our total CO2 equivalent emissions in million metric tons over time for business as usual, and our best case recycling scenario, where our best case scenario here is the largest cumulative CO2 emissions reduction relative to baseline. But we can see that it's like not actually doing that much. And especially if we compare it with incorporating ubiquitous current best practices into the like different regions. And so obviously like the lowest impact in each supply chain sector at the moment is already relying on pretty significant like process improvements and a fairly decarbonized energy system. And so it's not a small task getting the rest of the world to that best practice level. But it's still like fairly promising to see that we can achieve these sort of reductions with technologies that currently exist. And also we can see that if we combine that with our best case recycling scenario, we can actually get below 2018 emission values, which is still short of our like 2-degree warming targets, but it's a good start. And we can probably get closer by understanding why recycling isn't doing that much and increasing the amount that it does. And so the main thing is that in order to get a large reduction in CO2 emissions, we need a pretty large recycling increase. And so our displacement value only ends up being about 0.57 because we're having a large amount of rebound. The reduction in mining is not as large as the increase in the scrap supply. And so we're losing about 40% of our potential emissions reductions.
So just to clarify, the total CO2 emissions, this is not just from copper mining and copper related things, or is this just from copper related like industry?
Yeah, this is just copper as an industry.
Okay.
Which like by 2050 is expected to be around 3% of global like energy consumption. So it's a pretty small section. Copper is like the third most consumed material behind steel and aluminum, but steel is like a full order of magnitude greater, at least. So like this is sort of the thing where it's like, this is where we have data availability and a lot of industrial connections. So it makes sense to study this system. And hopefully these sorts of ideas are applicable to other materials too.
John, is there some sort of, I don't know, like a Moore's law or something for the quality of the recycling processes, or are they relatively stable?
I'm sorry, I don't remember which one Moore's law
Oh,
is.
in other words, will we be able to refine copper in a way that creates less pollution and costs less money tomorrow compared to today?
Generally, yes, but we're fairly close to like the thermodynamic limits on a lot of these things. So like we can expect like to get a cleaner smelter, but like our smelting technology is, you know, there's only like a small amount of improvement we can really make there beyond what's like actually possible. And so we need to either find ways to substitute the fuels that they're using, because a lot of the time they're burning coal and using like on-site coal-fired power plant generated electricity. So like a lot of it is more on the like input side at this point. And just like installing those actually good smelters and refineries like everywhere instead of just the places that have gone ahead and like built those low polluting smelters.
And then just one other question about, so the scrap copper that we're talking about, how much of that is like pure copper versus various like copper alloys and things? It seems like alloys would be a lot harder to recycle.
Yeah, alloys are a lot harder to recycle. I want to say that alloy is like roughly 30% of the market. And it's a fairly separate component of the market because so much of stuff is like brass is like copper that is alloyed with zinc up to like 40%. And bronze is also like copper alloyed with tin up to like, I think typically 20 to 30%. So like those sectors try to keep things as separate as they can. But yeah, it is hard.
Have you also done any specific analysis on the different cathode chemistries and how that affects the carbon intensity or like the carbon emissions, like LFP, LMO, NMC, like those cathode chemistries, to compare if that does like affect the different models?
So like for lithium ion batteries?
Yes.
Okay, yeah. We haven't, I guess I haven't quite gotten there yet. We have a visiting student this year who's like focusing really heavily on lithium ion batteries and lithium and like cathode chemistries. But we haven't gotten that far yet. Sorry.
No worries. Thank you.
One more question. If I understand the rebound effect correctly, so basically you produce more and that also increases your emission. But presumably those are made into new devices that also generate emissions. Is that also taken account in this best case, or would that be like an additional source of emissions on top of this?
I mean, we're taking into account like the additional manufacturing, like, of those new devices. I guess we're not counting like downstream, like we're not counting the emissions from the cars that contain this copper, but we are counting like the rolling and forming that's like needed to process the copper from an ingot into a wire or like tube or whatever.
Fair.
Cool. So yeah, I guess there's, you know, a lot of room to increase displacement, but the question then is how. So we looked at correlations between displacement and all of our various model parameters. But because we're analyzing a model, there's a whole bunch of interdependencies between all of our different model parameters. And so the regression results for trying to find this relationship were all multi-collinear and therefore fairly inconsistent. So we did a meta-analysis of many smaller models to get the mean effect of a given parameter. So for refining charges, we can see that it has this distribution of coefficients across all of our different models. And so it has a mean effect of about negative 0.0004. So increasing or decreasing a refining charge by 1% increases displacement by this very small number. Which, yeah, so it's really small. But we can see why, because decreasing refining charges has these two parallel effects on mining, and therefore displacement. So decreasing refining charges decreases the costs that mines have to pay, increases their profitability, incentivizes mines to produce more and stay open longer. But also from the refinery perspective, this lower refining charge means that they're not making as much money processing copper concentrate. And so they're going to shift toward recycling and decrease their demand for mined material and eventually decrease mining that way. And so this negative relationship indicates that we are following this lower pathway, and that this lower pathway dominates. And so if we can implement a policy that aligns with this pathway, like a carbon tax or some sort of minimum recycled content requirement, we can push displacement higher still. So to summarize, there's this simultaneous drive to decarbonize and increase consumption, but recycling can address both of these issues. There's also sort of a kind of constant debate of, you know, we need this much, like this huge increase in copper consumption, for example, to meet the needs of the renewable energy transition, but also as low-income countries modernize and gain access to electricity and indoor plumbing, that's also going to contribute to pretty significant increases in copper consumption. So that like 300% increase by 2050 rises to 350% under more equitable development scenarios. So like in some ways, this displacement causing increased material consumption is also serving like a different sustainable development goal. But we also find that understanding the economics of the system is key to understanding the environmental impacts of our changes in recycling, because if you don't, you pretty substantially overestimate the benefits of a given action, and the benefits of this sort of action and that we looked at here is a pretty mediocre best case scenario. But also we can find ways to understand why it's so mediocre and find ways to fix it, which is always encouraging. So yeah, thank you very much for your time and happy to answer any additional questions. and here are the two papers that we've put out with the copper side of things, in case you're interested in learning more about what we do.
John, this was awesome. Thank you so much. So many of you have been to our events before. For those of you who haven't, we run them very informally. So you should just go ahead and unmute and ask a question if you have one. We'll do our best to not speak over each other.
So have you modeled that if the displacement does increase, does the best case scenario get much better? Or like, does it become less mediocre at least?
Yeah, I mean, we haven't modeled it explicitly, but like I guess it would, since like when we break out those impacts into the different sectors, we can see that like mining is still a large fraction of that resulting impact. So like if we can decrease that wedge, we can decrease the overall emissions. There's going like saying that the like 57% displacement means that we're losing 43% of our like emissions benefits is not quite right, because like as we saw, like copper still takes 15% of the energy of primary material to recycle it. So like I guess we have sort of diminishing returns on environmental impact reduction as we increase displacement, because we're still going to have like the impacts of manufacturing are pretty significant, that are going to be there regardless of where our material is coming from. I don't know if that answered your question in the right way. But...
I see your point.
John, you said this was the third most popular metal, right?
Yeah.
So with regards to the other two, what are variables, things, I don't know, anything that makes them different from copper? Like, is there any difference in the impact of mining them? Is there any difference in how they're used, or are they just directly comparable across the board?
Yeah, no, they're not. I honestly, I don't know a ton about the steel system because I haven't studied it very much. But for, well, I guess it's fairly true for steel that like you are more restricted in your ability to directly remelt scrap. Pretty much everything ends up going into a refinery in some form to remove impurities. But they also sort of suffer from this like accumulation of certain impurities because thermodynamically it's really hard to remove copper from steel. Like copper can be really easily refined because steel can be removed from copper, but the other way around is pretty hard. But for aluminum, like the oxidized version of aluminum is so stable that you can't actually, at least through oxidation, remove any of the other major contaminants. So directly remelting, or I guess directly remelting aluminum is the only option. Like you can't, like we just don't have refineries that are really equipped to handle it, because the refining of aluminum from mined, like bauxite is the mineral that we get aluminum from, and then process it to aluminum oxide, and then we like fluorinate it, change it into a fluorine-based compound, and can then do electrochemistry on it to extract the aluminum as an element. But like we can't feed scrap into that system well, so the aluminum system relies entirely on taking scrap and diluting out like any impurity elements, so you end up with a pretty different like blending optimization model there. Those are like the two major differences I can think of. I guess in terms of environmental impacts, actually, aluminum is quite interesting because, well, and iron is too. They both have really high ore grades. Like copper, the average ore grade is about 1%. For bauxite and iron ore, it's up closer to 50%, like 30 to 50%. And so the mining process, it's still this like, open pit, pretty environmentally damaging in a local area, but like the refining processes are much less intensive, or at least like the grinding and everything to concentrate it is really not super intensive. So like for aluminum, this like fluorination and electrochemical processing is the like by far the most energy and emissions intensive component. So the smelting process. So like for copper, like mining is the biggest chunk of the emissions, and then there's like refining on top of it. But for aluminum, it's kind of the other way around.
Can I ask a question?
Yeah.
Okay, well, thank you for the talk and the research, John. One thing I'm curious about is I've seen a lot of people who go from straight out climate denial to a type of like climate hopeless person, where it's like, oh, sure, climate change is happening, and I've known that the whole time, but what can we even do about it? What would you say to people who sort of look at your research and say, hey, even when we have the best intentions, it doesn't actually do that much because people will use more or there are other issues in the process? What would you say to those types of people, given the work you're doing?
Yeah, I mean, it's definitely like, I definitely struggle a bit with that issue too, in terms of like working in climate. You end up with like some frustration about how things are and how things are changing at too slow of a pace. But like for recycling, for example, like even if it's not doing as much as we want it to in terms of emissions reduction, it's still doing other good things in terms of like allowing people access to electricity and indoor plumbing. And so like looking at the like UN Sustainable Development Goals, you've got, you know, like only one of those is like really CO2 related specifically, out of like the 15. And so, you know, we can make progress in other ways. And generally, like regardless of how much the recycling is doing, increasing recycling is still going to bring down the like emissions per copper required. So like, I guess I find a little bit of hope in that. And I guess like a lot of the policy solutions to driving displacement higher are also things that like would address these like rebound effects and issues with consumers. So like, yeah, it's sort of a like we need all of the above in terms of efforts on this front.
Awesome. So kind of a sure, it's not a panacea, but it's still necessary.
I mean, yeah.
Okay,
Like,
cool.
yeah, even if you're not getting as much benefit out of it as you like theoretically could, it's still better than not doing anything.
Cool, thank you.
Yeah.
John, if you ignore the CO2 aspect and the like global warming aspect and think about other climate aspects, like for instance, pollution that it has health consequences for people, how does recycling compare to mining?
Yeah, it's actually really interesting. Like the motivating factor of this China study is the solid waste ban was like done to stop other forms of pollution within China, like smog and particulate matter emissions that were coming from processing this like low grade copper scrap. Particularly like electronics are a big issue because it's just like, and I guess wiring too, which is like 70% of copper goes into wiring in some way. And so like since wiring is always like coated in plastic, they're typically like the easiest way of dealing with that is just burning it off, which like has CO2 emissions, but also in terms of like localized pollution is really harmful. So like their goal in this solid waste import ban was to decrease local like smog and particulate matter related pollution. And what we found was that like when you limit the amount of scrap that can come in, it causes you to increase the amount of mined material that you import instead, so that the refineries within China could still meet their production goals. And because with scrap, you're going from like something that is 50 to 60 to like 90 to 100% copper, like even the low grade stuff is still higher grade than like copper concentrate is. And so it still has like this importing of additional concentrate and the environmental impacts associated with primary refining were outweighing the benefits of reducing scrap imports. And so like our recommendation there was that China also restrict its imports of mined material and start importing things like higher up the chain, basically, if they wanted to like fully address these localized pollution issues. And like while our paper was in preprint, they actually did that. So I don't think that there's like enough to say that like we actually helped, but it was still cool to like see the policy align with like our findings, I guess.
How do geopolitics impact the cost and availability of these types of materials? Like, has the war in Ukraine had any sort of impact on the variables you take into account in your model?
We haven't tried to model that sort of thing quite yet, I guess. Like, sort of the goal is to remove as many of those external influences as possible. So like when we do our like regressions of price, we typically have oil price as a additional regressor to eliminate all of those like politically influencing like factors, so that we can just see what supply and demand are causing. But like, I guess as an example, Russia is a huge producer of nickel, and so nickel prices have spiked a ton recently due to the war in Ukraine and the resulting sanctions on Russia. So like, and nickel is used also in at least, I don't know if it's most, but several lithium-ion battery cathode chemistries. So like, yeah, it definitely affects things. And I guess a similar one is like Chile has been fairly slow in terms of allowing additional lithium mining to happen, because a lot of lithium mining is happening in Chile. And with like the rapid rise in electric vehicles in the last couple of years, demand for lithium has spiked, and the mines haven't been able to keep up with it. And so it rose like a factor of 10 over the last couple, like the price of lithium rose like 830% is the number I most recently saw over about a year and a half. So like, yeah, these like even fairly small decisions on the geopolitical level can have pretty significant impacts on the price. And yeah.
Hey, John, I have a question. In plastics recycling, there's often kind of this deficit for the end user due to high exposures to chemicals such as BPA in the product after recycling. Are there risks to users when it's metals recycling too in a similar way?
Sorry, it cut out for a second there. Could you repeat that?
Sure, yeah. So in plastic recycling, oftentimes the process of recycling it will actually result in a breakdown in the plastics, causing more exposures in a dangerous way for humans. And then the end user is essentially toxicologically compromised. And I'm asking, in metals recycling, specifically with copper that you were talking about, is that a risk of the process? Is that something that you guys are also looking at when you think about how to optimize it in the process of recycling?
Yeah, so luckily with metals, that's not a concern, since like copper is just the pure elemental copper, and the contaminants associated with it are just like other metallic elements. So like you would have maybe an additional 0.001% zinc or something in a recycled product, but like since we're reaching these alloy compositions no matter what. It's just like an elemental difference. And so like for plastic, since it's all these like long chains of molecules, having that degradation is much more impactful. We have someone in our group who studies different plastic recycling, I guess, policy and like processes. And yeah, I do not envy her job.
Where is the copper?
A lot of the copper mining, at least, is in Chile. I want to say they're like 60% of global copper mine production. And then Australia has a bunch too. I don't remember who all else.
Does it matter what the source of the scrap is, like specifically like for household appliance, right? Is that sort of harder to refine? Is that even a big component?
It's like, it definitely depends a lot on what, like, I guess for things that are just like pure copper, like electrical wiring within an appliance, like that's easier to deal with, I guess. But like different products use different alloy compositions. So like all of our like all of our plumbing is all like brass piping. And yeah, I mean, like it all depends on the composition to some extent. And then like dismantling is always sort of a struggle too. Like looking at the recycling infrastructure like within Massachusetts, like they're like all the recycling gets processed by like a big recycling facility that's like using, I think, mostly infrared to categorize different things. So like black plastic doesn't actually get picked up, and so it just gets treated as trash. But like the reason that we, or like part of the reason that we ship our recycling to lower income countries is that like they have this cheaper source of human labor, and hand sorting recycling is way more effective. And so that's just a like fun problematic thing. Because like when China stopped its solid waste imports, like it just got redistributed to other countries in Southeast Asia, and they've been flooded with waste, basically. And so they've been trying to impose their own bans. And sorry, got on a bit of a tangent there. I don't know if I totally answered the question.
No. All the tangents also like very informative. Don't worry. But yeah, I like, as someone growing up in Mumbai, like I've seen like the recycling pile. It is like, I don't know, like ethical like dilemma also. Like, how do you recycle effectively? I guess.
Sorry, the audio kept going in and out there. Could you?
Oh, I'm sorry. I was just saying that I grew up in Mumbai and I've sort of seen the recycling piles, and it is a whole ethical dilemma, I would say.
Yeah, for sure.
Well, maybe we should wrap up pretty soon, but John, this is terrific. And I guess maybe a good thing to end on would be, what are you working on next? What's kind of the new exciting thing in the world of you figuring out how doomed we are? I mean, what's your next exciting project, if you can talk about that?
Yeah, it's sort of diving into that question that you asked about the differences between materials and their supply chains. We're trying to develop a more general model that we can sort of apply to any material, and eventually expand it to materials that are only produced as byproducts of other metals, like all of the cobalt that we use for lithium ion batteries. Only about 1% of it is mined as like a mine that is going after cobalt as their primary thing. And then like 50 to 60% is mined as a byproduct of copper mines, actually. And so when you have a system, like when it's a byproduct material, that means that the mine doesn't get as much, like only gets some fraction, like fairly small fraction of its revenue from that commodity. So like in the case of cobalt, if we can't meet demand for cobalt and lithium ion batteries, the price can rise, but the price rising may not actually affect how much cobalt we produce, because the mines, like the cobalt's not a big enough fraction of their revenue to affect their behavior. And so we're trying to understand how that works, because so many of the metals that we need for like solar cells and for wind turbines, like are byproduct materials. So understanding how the mining associated with them works, and in effect, like how increasing recycling within those sectors can affect mining, is sort of like an unanswered question in the field. So that's our sort of next direction, I guess.
Very cool. Awesome. Thank you so much, John. If people have questions, I imagine they can email you at your MIT email address shown here.
Yeah.
And I'll post this video online sometime later today. So if anybody wants to revisit material, or if their internet connection dropped or whatever, they can do so. So thank you so much for your time, and I look forward to climbing again when I see you in September.
Yeah, cool. Thanks for having me.
Okay, adios.
Thank you.